Good morning, guys. You've made it to the last section of Chapter 8, that is 8.10. I'd like you to try this warm-up problem, if you would. Hit pause, work it, and then hit play, and we'll check it. I'm going to work it right now. All right, so the first thing I want to do is begin to rewrite f of x so that it is centered at -3. I've got f of x is equal to 1 over, this is -5, plus 2 times x plus 3. That's the way I'm going to ensure that my r is actually centered at -3. Now, again, you got to keep it balanced, just like you would if you were completing the square. So I really just added on 6. Now I want to take 6 away. I really added 6, so now I take 6 away, and then I just simplify it. So this gives me 1 over, this is -11 plus 2 times x plus 3. Now I need to divide everything by -11 because I need this first term here to be 1, because it is a sub 1 over 1 minus r. That means now my f of x, I don't want red, this gives me f of x then is equal to -1/11 over 1 minus 2/11 x plus 3. All right. Now I've got a sub 1 over 1 minus r form, so now I'm going to put it in summation form, n equals 0 to infinity. This is -1/11 on the outside. That is a constant multiple, and my r is 2/11 times x plus 3, all of that to the nth power. Now, if you recall, we just built a power series that is in fact an infinite geometric series. So I know my r, this is my r, the absolute value of that r has to be less than 1 in order for this power series to converge. That only happens when I'm using a friendly form from section 8.9, that is a sub 1 over 1 minus r. So I know for a fact that my absolute value of 2/11 times x plus 3 must be less than 1. So I've got 2/11 x plus 3 less than 1, 2/11 x plus 3 greater than -1. So that is x plus 3 is equal to 11/2. X plus 3, I should say that's less than, greater than -11/2. And I want to add then 6/2. Take away 6/2 from both sides. So x is less than 5/2, and then I want to take away 6/2 here. So x is greater than -17/2. So my interval of convergence here, because this is a geometric series, gives me an interval of convergence that ranges from -17/2 to 5/2, not including the endpoints because of the geometric series test. All right, on to 8. And 8.10 is entitled Taylor and MacLauren series. It's really just more work with power series. So it's already things that you're familiar with. Now there are 3 formulas that you need to know. I was going to say that you have to memorize, but clearly that's not going to happen. These are listed on page 638 of your book. And the 3 that we're going to primarily be working with are e to the x, sine x, and cosine of x. These are all listed again on page 638. There's these 3, and I think it's helpful to have memorized not only the first few finite terms, but also the power series notation in summation form out here at the end. So again, since the test is open book, open note, I'd make sure that you get those written down, or just have access to page 638. I'm going to show you then how to use this. Really, it's tied in very closely with the functional notation that we used in the previous section when we were coming up with power series for things like the arctan of x to the 4th, or the arctan of x to the 4th all over x cubed. Exactly the same thing is going to happen in this section, so this section should be fairly straightforward. Let's work a couple of examples. So for instance, if f of x is equal to e to the x, given this power series, again, that's already been given, page 638. If I am looking for the power series of, let's say, f of x is equal to, actually, let me change the notation here slightly. Let's call this g of x is equal to e to the negative x squared. It's super easy to do. So if f of x is equal to e to the x, then I think you could say that g of x is, in this case, is really equal to f of negative x squared. It is e to the x with negative x squared replacing your x function. So all I do is take f of x, and this is functionally notated, so negative x squared goes in wherever you see an x in the original f. This is now the sum from n equals 0 to infinity of negative x squared to the n all over n factorial. And then, of course, I would like you to clean this up. This is the sum from n equals 0 to infinity. This is negative 1 to the n, x to the 2n, all over n factorial. Then if I asked you for, say, the first few finite terms, you would just take the direction manual that you just generated and write out the first few finite terms and simplify them. But it is easy as that. All right, so this then turns out to be x cubed times f of negative x to the fourth, much like the previous example. So I'm going to start off by just building this right here. This is then the sum from n equals, that looks horrible. There we go. This is the, amazing, 0 to infinity. This is negative x to the fourth, then to the n, all over n factorial. And then, of course, every single term is multiplied by x cubed. That gives me another x cubed in the top here. So I'm just going to clean this up and separate off the alternating part. This is the sum from n equals 0 to negative 1 to the nth. This is then x to the 4n plus 3 all over n factorial. And that then is my power series in summation notation for g of x, which was what was asked for originally. All right, and then the same technique applies for the sine and the cosine. So again, we're just going to work with primarily those three. I'm limiting those three because that's typically what I do in a classroom when classes are meant to memorize those formulas, but of course, that is not going to apply to you. Now, the other thing I'm going to have you work on is, this looks a little bit, and it's a little bit difficult to catch on to, so let me know if you have questions. If I'm looking for the first three non-zero terms of the product of e to the x and cosine of x, now I believe it is far easier to work with the first few finite terms of each one of these strings rather than use the summation notation because you can kind of visualize what's happening here. So here's what we're going to do. If I took these infinite power series sums and I started multiplying them out, or even if I just limited e to the x to the fourth power and cosine of x to the sixth power, and I just took what's listed here in parentheses in green, what I would need to do is begin to box these out or FOIL this out. So rather than write out this gigantic box, what I can do is just start to visualize how this product will come together and think of these terms in ascending powers, because each of these strings are written in ascending powers. All right, so first thing I want to think about is there a way to multiply terms, or a term rather, of e to the x with a term of cosine of x so that I get a linear function, that is x to the 0 power? Sure, I can take 1 times 1 and multiply those together. So the first non-zero term of my product, let's call this h of x. Oh, I already called it h of x. So h of x is equal to e to the x. Cosine of x will be equal to 1. In fact, if I was making a large multiplication box out of this, the upper left-hand corner of the box would be 1 times 1. That would give me 1. So I'm good. I need 2 more. Now I need to think if there's a way to multiply any one of the terms in the e to the x with any one of the terms in cosine of x in such a way that I would get a linear term. Now, the first one is a constant. I called it the linear term before. I was mistaken. So this is the constant term. Now I'm looking for a linear term that is x to the first. And there is a way. If I multiply x in this string with 1 in this string, I get x to the first power times 1. So what I'm going to do is add that term then on to my 1. So now I have a constant term, I have a linear term, and by the way, that is the only way to multiply terms from either one of these together to get a linear term. Okay, now let's look for a quadratic term that is second power. So is there a way to multiply any terms from e to the x with cosine of x that I end up with a second degree term? And we can do this in blue. Yeah, there's a couple of ways. First of all, I could take this one right here, x squared over 2 factorial times 1. So I'm going to go ahead and write that down here. So this is going to be plus, this is x squared over 2 factorial times 1. And then it looks like also I could take x squared over 2 factorial from the cosine and multiply it by 1 in e to the x. So that will give me minus x squared over 2 factorial. And I think that's the only way I'm going to come up with a quadratic term. The problem with that is those cancel and they give me a 0 term. I'm only looking for non-zero terms, so that's not going to help. All right, now let's look and examine terms in e to the x and cosine of x to see if there's a way to multiply them together such that I get a third degree term. All right. There's a couple of ways to do this. Let's do this in green. I'm looking for a third degree. It looks like I can take x and from e to the x and multiply it by this term right here. That will give me a third degree. So that's going to give me plus, what is that, x cubed over 2 factorial. And that needs to be negative, or I can just do this, plus negative x cubed over 2 factorial. All right, I could also do this. I could take x cubed over 3 factorial times 1. Let's go ahead and write that down. That's going to be plus x cubed over 3 factorial. And I think that's the only way, those two combinations are the only way that I'm going to get a third degree term. So I think that could be my last non-zero term. So what is this? This is going to be plus. This is negative x cubed over 2 plus x cubed over 6. I get a common denominator of 6. That is a negative 3x cubed plus x cubed over 6. So the first three non-zero terms are going to be 1 plus x. This is going to be equal to minus 2x cubed over 6, aka 1 plus x minus x cubed over 3. That is my first three non-zero terms of the product of e to the x times the cosine of x. All right, one last thing I want to show you before I cut you guys loose on 8.10. I'm also going to have you work on some power series review, and power series specifically that require you to use integration or differentiation to come up with the power series of what you're looking for. So for instance, and this ties back into 8.9, that I'm looking for the power series representation of that original function, that is the arctan of x cubed over x to the fourth. I believe I went through a problem similar to this in 8.9, but what I want to do is focus first just on this numerator here. Because I know that if I derive arctan, it puts it into a fairly friendly form that I can work with and develop a power series for. I then just multiply the denominator of that power series, once I've integrated it, to get by x to the fourth to come up with my final answer. Hopefully that's clear. Check this out. What I'm going to do is then just look at the numerator and I'm going to derive it. So for the time being, I'm going to say that, say, g of x is equal to the arctan of x cubed. and I'm going to then derive it, because that will put it into a friendly form. That is 1 over 1 plus what I'm arctaning squared times the derivative of what I'm arctaning. This then becomes g prime of x is equal to 3x squared over 1 plus x to the 6th. It's a really friendly form, so check this out. The power series notation for g prime of x goes from 0 to infinity. I've got my a sub 1, put the 3 out front, I've got x squared here, times my r, which is negative x to the 6 to the nth. Now, here's the point I'm trying to make, or the point I'm trying to emphasize. You must simplify that power series before integrating. Let me say this again. You must simplify before integrating. So don't integrate it in this form right there. You must simplify it first. So let's put this right up here. This is 3 then times the sum from n equals 0 to infinity. This is going to be negative 1 to the n, and this is going to be x to the 6n plus 2. This form right here is all right to integrate. Now again, I need to integrate it because this underlined portion right here is not the power series for the arctan of x cubed. It's a power series for the derivative of the arctan of x cubed. In order to get what I need, that is the power series for the arctangent of x cubed, I must integrate that. All right, so now I've simplified it, so I'm going to get rid of this rule here. Get rid of these silly arrows, and I'm going to integrate it. All right, so here we go. I have 3 times the sum from n equals 0 to infinity. This is negative 1 to the n. This is x to the 6n plus 2 plus 1, all over 6n plus 3. And again, it doesn't come up in these problems, but if you check x equals 0, you get 0 on both sides, so c does turn out to be 0. I'm not going to have you worry about the c value right now, so you can forget about it. All right, so this is the power series then for just the numerator. If I am looking for the power series of f of x, I think you might agree that that is the same as g of x divided by x to the 4th. This is the power series for g of x. If I multiply that by 1 over x to the 4th, I've got it. So, change this notation here. All I want to do then is take this power series. This, of course, is, again, g of x. What I'm looking for then is g of x over x to the 4th, which gives me 3 times the sum from n equals 0 to infinity, negative 1 to the n, x to the 6n plus 3, all over 6n plus 3 times x to the 4th, which simplifies to 3 times the sum from n equals 0 to infinity, negative 1 to the n, x to the 6n minus 1, all over 6n plus 3. As an alternative, you could pull a 3 out of here. That would give you 2n plus 1, which is probably what you'll see in the solutions manual. All right, so got a worksheet for you to do. I may PDF that to you, maybe in the workbook. I'll let you know. Good luck, guys. Stay strong. We're almost there.